Get started. All right, so hello, my name's James MacGlashan. I'm a postdoc here at Brown, filling in for Stephanie for today. So for today, I'm going to be doing a talk that's kind of a mix between a research talk and maybe kind of lecture-y and hopefully interactive. So please either ask questions, or if I ask a question, answer it if you'd like to. That'd be great. So the topic of this talk is reward functions at the center. And so the basic idea behind this is that intelligent agents generally need to solve a lot of different problems before they can behave in the world. But in MDP research, you tend to assume, oh, well, we have a reward function, and we're just going to do planning and learning, and that's it, we're done. There's all kinds of other issues you actually need to address before you can even get there. So in particular, you need to maybe not assume that reward functions are just an input that are given, but they have to come from somewhere. So in this kind of talk, where I'm going to go over learning from demonstration, which gets you reward functions, or learning from human feedback, grounding language, and maybe even evolving ethical norms, and how reward functions are just like the centerpiece for doing all of these things. OK, so my understanding is you guys have gone over MDPs and planning and reinforcement learning, right? So this should hopefully be a review. An MDP, or markup decision process, is this 5-tuple. The number of things in the tuple sometimes varies between which work you're looking at, and we'll vary this even further. But the kind of core things you tend to have are, you have a set of states in the world, a set of actions your agent can take, these transition probabilities that say, if I took this action in this state, what state would I end up going to? And it can be stochastic, so it doesn't have to deterministically always go to the same next state. And there's this reward function, which basically tells you how much it gives you this signal for things you like or don't like every time you transition through the world. And then you have this discount factor typically, which is kind of how much you value distant rewards in the future or versus near rewards that could happen maybe in the next time step or not. Does that all sound familiar to you guys? Yeah, OK, cool. So what are the common things you do with MDPs, right? We're generally looking to build a policy, right? And the policy is some mapping from states to action. The agent can then just follow, and we're trying to find a policy that maximizes the cumulative reward over time, right? So what are some ways we can get that policy? Can I give some examples? Be high-level examples. All right. So one way is planning, right? We can sit there, we have everything, we do planning, we get a policy out. Another way is learning, so that's reinforcement learning. And we do learning and we get a policy out. OK, either way we're getting policy outs is the typical thing. This is kind of an important distinction that a lot of experts even don't understand. Planning and reinforcement learning are two different things. They kind of define the problem differently, or there's a different problem you have to solve. Can anyone guess what the distinction here is? If you've read about all this stuff, you should be able to figure it out, but it's strangely not obvious. Yeah. Yeah. So in particular, the last part you said there, your belief of the transition is kind of the key part. So in RL, we don't have the transition model, right? So we have this MDP, but we don't have T. And we actually don't have R either. We're just dropped in the world. And we have to figure out how to behave just by interacting with the world. And every time we take a step, well, that's the step we now have to deal with. So if I made a terrible decision, I'm going to have to suck it up and keep going from there. Planning, in contrast, is like saying, well, I know what the transition ranks are. I know how the world works. And so if I want to figure out how to behave, I just sit there and I think really hard for a long time. And I'm like, yes, I've simulated it. I now know that this kind of behavior is going to give me lots of rewards, so I'm going to do that. So there are two different kind of problems, because in one, you have to stick with your decisions. And if you're simulating, you can start thinking about going one path, and you're like, oh, that doesn't look so good. And you can back up, right? Because it's all in your head. It's not real, right? So important distinction, you tend to apply different algorithms for each of these things. So just to kind of drill this home, I'd like to give an example. Yeah, you have a question?
So if RL doesn't have the transition model or the reward, in what ways does it make it better than
It's not better than planning. It's just a different problem, right? So ideally, we'd like to have the transition dynamics, right? If we had the transition dynamics, we should just plan, right? Or we should do some combination of some maybe finite horizon plan where we spend some amount of computation time doing it. So learning is strictly a harder problem because we just don't have as much information. OK, so let's let's do an example to drill this home. So how many of you have heard of burlap? Stephanie may have mentioned. So Dillip knows. So here at Brown, we're developing a planning and reinforcement learning library called burlap. And you can do all kinds of RL or planning things with MDPs with it. So I'm going to be using that a lot for a bunch of examples. And so if you like planning and RL, you should check it out. So let's do an example. Because my resolution is really tiny, everything is going to be squashed in bizarre aspect ratios. So sorry. All right. So in this example, you guys are going to be the learning agent. Right? This is kind of what it's like to be an RL agent. This is the world. This is the state of the current world. You have actions 1 through 6. Go. So someone tell me what action you want me to do, and I will enter it. You can choose action 1 through 6. 2. 1. 6. 5. 3. 4. 3. 1. 2. 2 again. 3. 3. 2. 2. 5. We're not done yet. You'll know when you're done. 5 again. 5. 6. 5. 1. 1. 1. 1. What was the next one? 3. 6. 1. I heard a 4 and a 2. I will press them both. It did not work. You will know. If you don't, it will be extremely obvious. What? 1, 3. I heard 3, 4. I heard 2. 2. 4. 4. 4. 1, 1. Victory, and it's kind of scrolled off the screen because of the aspect ratio. OK, good. So you figured it out. That's what it's like to be a reinforcement learning agent. In fact, reinforcement learning agents are in some sense harder because you're probably pooling from all kinds of background knowledge you have. You know there's this spatial information. So you kind of got, OK, 1 is going north, and 2 is going south. You just immediately compressed it. An RL agent doesn't usually, in the typical way, doesn't have that information. It's just kind of in the world, and it's well, in this state, I went south, but maybe in this state, I'll go east when I apply that action. It just doesn't have this kind of structural information. And through your learning over time, you've kind of built these models, and you have these beliefs about how things should work. That's a red circle. Maybe it goes in the red square. That's even something you're kind of getting. It has no notion of color. So RL is just very, very, very hard. And so I hope that kind of captured it. In planning, though, if I told you, well, you can go north, south, east, west. You can pick up one of these circles. You can put them back down. And the goal is to get the red circle into the red box. If you knew all this information like you would in planning, it'd be OK. You go north, you go south, south, east, east, east. You pick up, it'd just be easy to solve this because you can just do it all in your head. But RL knows nothing. And so if you ever look in RL and you're man, it's taking forever to learn how to do anything. It's yeah, it's actually really, really hard to do these things. So brief diversion with this just to kind of illustrate the difference between RL and planning, because it's an important distinction about how you go about solving problems in the future. OK, cool. Boom, 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 boom. OK, so we had our MDP. Oh, yeah, you have a question?
So what would make planning different from just a normal search problem?
It is a search problem, actually. It's very much a search problem. And there's different ways you can handle a search. So MDP, if you're thinking about classic, like A star, for example, A star doesn't work in MDPs because it's still, you can't assume determinism, right? And it's always saying, well, if I apply this, I'm always going to go there. So there's a different suite of things. So dynamic programming and value iteration is one way of handling that. But it's absolutely a search problem. OK, so this is kind of better factoring. In my opinion, a bunch of us here are trying to make this like the new norm. It's common in classic deterministic planning, this kind of framework, but not so much in MDP. So the idea here is we're going to kind of differentiate an MDP into two different parts. We're going to have a domain, which kind of defines what the world is and how it works. So you have your states, you have your actions, and you have like the physics, which are the transition dynamics. But then you can have different tasks in that same domain, right? I can have a task where I'm taking that red circle to the red box, or I could be taking a green circle to a green box, or a blue box, for that matter, right? And furthermore, there's kind of this interesting different parsing, which is it's sometimes useful if you have these different tasks to represent terminal states explicitly. So does anyone know what a terminal state is when I say that? I mean, the idea is it's like all action stops. You reach the state, game over, you can't do anything further anymore. And when we're talking about tasks, what ends the task is kind of changes what those terminal states effectively are. So it's useful to think about we also have this set of terminal states we'll define for the task. And our discount factor also kind of defines the thing we're trying to solve. Because if I'm really myopic and just care about the immediate things, that's a different problem than when I care about the far distant future things. OK, so the interesting thing about terminal states is we might say, well, imagine a world that has no terminal state. It never ends. It keeps going on forever. Can we kind of unify these two ways of thinking about, well, I do these things until this point, and these things go on forever? And it turns out there's a really nice transformation. So this is kind of a representation introduced by Sletton and Bartow in the book Reinforcement Learning Introduction. And the idea here is you have each of these states. And this gray box here is a terminal state. And the way we represent this as if it's just going on forever is you get reward along the way, and then you hit the terminal state. And then you're just deterministically always forced to go back to the terminal state, and you get 0 reward, right? Which matches perfectly with the idea of everything ends when I reach this terminal state. So that's a good way to think about the math, about what's going on. And that's often why you don't have terminal states an explicit thing in the MDP, because you think about them as being baked into the transition dynamics and reward function. But it's more useful to think about them as a thing. So I kind of want to address this. Like getting this notion of terminal states and reward functions is kind of important because the rest of the talk we're going to be talking about how you use those things. So you all have the Russell Norvig AI book. It's a great book. And they have a bit on MDPs and value iteration, right? So they define this kind of grid world. We can like move north, south, east, or west. It's kind of stochastic. Sometimes you don't go where you intend. And you tend to get like minus 0.04 reward everywhere for the states you leave. And then when you get to these +1 or -1, those are supposed to be terminal states where you get this reward and everything ends. So this is on the right here, we have what the value function they say it is. So we can take burlap, and we can run this. There we go. We can have it run value iteration just like them and see what we get. And so if you look at this versus this, I can't really switch back because the resolution very easily. These numbers don't match up. So does anyone know why they don't match up? All right. So the issue here is the Russell Norvig MDP is kind of broken, unfortunately. And we're going to try and get them to fix it. They had this very non-standard definition of reward functions and terminal states that they use in their book, which is they had this notion that I'm in a state, and when I leave that state, I get the reward for that state. And so I keep getting this minus 0.04, even when I transition to this goal state. And then it's not actually a terminal state. I get one more time step where I get to leave that terminal state to this imaginary hidden state that's actually a terminal state, gives me 0 reward, and everything goes from there. So it's not really a terminal state, and it doesn't really match with how most literature works. So understanding this difference is actually kind of critical. The conventional kind of way of thinking about this in a grid world in standard literature is, no, this is a terminal state. So, and my reward function is going to give me reward for transitioning to good places. So here, this is a bad place, so I get a cost. I transition to here, get a cost, get a cost, get a cost. And then I go to my goal state, I get the reward, and then I get 0 thereafter, just transitioning back to like a terminal state. So this is the more conventional thing. This is the way burlap does things, and that's why you can see these differences in value functions. So the main point is just to kind of encode in your head that terminal states are like these things where everything ends from there on out. OK. So now we've kind of talked about classic MDP things, how you do planning and learning, what terminal states are. But the question is, where do these tasks come from? Right? In a lot of literature with MDPs, we just assume it's there. It's the input, and we're just finding the policy. That's our goal. That's all that matters. But that's really not the whole story for intelligent agents. These tasks have to come from somewhere. So one place they might come from is from humans. Right? Some human has some task that they want a robot to do, for example. Or maybe another robot wants another robot to do something. That'd be kind of weird, but we might do something like that. And it has to communicate these tasks in some way. So one way a human might try and convey the task is just by demonstrating themselves doing it to have the robot figure out what the task is. Another way is we might reward and punish like a dog, right? So you have a dog, you want to train it to do something, you reward and punish it until it does the right thing. Or finally, it'd be nice if we just communicate through our language what the task is and have the robot understand it. And then the other side is we can also think about evolution, right? Which is an agent's born. Learning is generally useful in the world, I think. So evolution then has to select reward functions in the agent's head that motivate it to good behavior. So evolution might be another path. So I don't know how far we're going to get through this talk, but if by some miracle we get through all of it, we'll cover all these topics. So we'll see how we do. OK, so first we're going to attack that first branch, which is learning from humans. So right, ultimately, we want robots to do things for us. But programming is hard. So burlap is great, but the average person is not going to program a reward function which examines the state features and all the complex things to define the task. It's just not going to happen. So we want to be able to convey our wishes to robots in a better way. So one way is by demonstration, right? So what we'd like to do is I want some robot to be able to carry out the things I want, and I'll be like, oh, well, the thing I want you to do is kind of like this, and I show them like what I do, and I guess I'm running around the podium, and that's the task. And it should be able to figure out the idea. It's like, oh, there's some reward function that inspires that behavior. I'll do that. And then the robot could then just go off and do that on its own for a while. There's other nice properties about learning from demonstration in that it kind of allows you to have friendly robots, right? So a robot can just kind of be watching you act in the world, and they can figure out what it is you're trying to do and then just actively help you without you requesting anything. So this has a lot of potential uses that make it very nice. And the other nice thing about learning this reward function is, unlike training a robot to mimic exactly how you behave, if it understands your wishes, it can generalize to new environments. Right? So if I change the way the world looks, it knows how to act because it knows the actual thing you're trying to accomplish. So getting the reward function out is very useful in that way. OK, so this is kind of the way to contrast inverse reinforcement learning from standard planning, for example. So the planning system you can imagine here on the left, which is we take a domain, we take a task, we throw them into a planning algorithm. The planning algorithm spits out a policy. And then if you have some initial state, the agent just follows the policy and acts in the world, and everything's great. So you get this behavior sequence of states and actions from the policy. Right? Inverse reinforcement learning, so it's inverted. Right? The idea is we have some domain, and I'll show you a bunch of state and action trajectories. And from those, figure out what the task was. And then once you figure out the task, you can actually do planning in other environments and do it yourself. But we're kind of doing this inverted situation here. So let's kind of give an example of this problem. We'll see how this works. I cannot find, oh, right. I'm going to want to do that. So here's another squashed world. And I'm going to act in the world. So that's one example. Let's try some from somewhere else. That's another example. Can anyone have done inverse reinforcement learning in their head and tell me what task I was trying to do? Yeah. Get to purple. Good. Anything else? And avoid the blue. In fact, I can walk through the blue, but I was avoiding them. Yeah, so that's a reasonable inference. And so that's pretty good, right? I gave you 2 examples, and you kind of figured out it looks like these were the goals, was get to purple and avoid the blue. All right, good. So we can do IRL. That's nice. So we want our algorithms to do IRL. OK, so how do we go about solving this? So I'll give a little groundwork first. Let's assume, for example, that the reward function that we're trying to infer from behavior is some factored model, right? So we have some set of state features in the world, and let's say the reward function is some linear combination of those state features, but we don't know what it is. So this will kind of define the space of possible reward functions we have, but we don't yet know what it is. And one nice thing about this, we have these state features, is it generalizes to new states, right? Because we have high-level features that describe various properties of the world. OK. So how can we find a reward function that motivates this behavior? Let me see. Right. Does anyone have any thoughts? All right. That's fine. So one way is maximum likelihood inverse reinforcement learning. So what we'll first do is we'll imagine, typically in a lot of MDP stuff we imagine we have a deterministic policy, right? Which says, for this state, I'm always going to take this action. And that's all well and good. In RL, sometimes we have stochastic policies because we want the agent to explore. So a stochastic policy says, for this given state, I'll give you a probability distribution over actions about which ones you should take in that state. So if we assume we had this policy, or if we can create a stochastic policy, then what we might want to do is find a reward function that would maximize the likelihood of our observed behavior under some policy. If we derive the policy from that reward function, we want to maximize the likelihood of our observations of state action pairs. Does that kind of make sense? Right? So like if we go back to my example, let's maybe go back here. Right? Let's say I'll stay down here. If I go up from there, well, there's a policy. If the policy says avoid blue and go to purple, that's the right behavior, right? We'd expect a high probability under that reward function. If the probability, or if the reward function, though, were blue's great, go through blue and hit purple, we wouldn't expect that. That'd be a low probability event. So these different reward functions would induce these different stochastic policies, and we compute different likelihoods for them. So we want to find the policy based on that's derived from some reward function that would maximize the likelihood of all of our observations. OK, so first we need a stochastic policy. Have any of you seen this kind of policy? This is called a Boltzmann policy or softmax policy. All right, so the idea here is, imagine we had our Q values, right? Normally, the kind of classic thing you would do if you did planning was say, we have a bunch of Q values that represent the utility of taking any action in any given state. And so the policy is take the action that has the highest expected utility, right? That's the good thing you want to do. So this Boltzmann or softmax policy does this exponentiation thing. And what it does is it gives you back a probability distribution where the action with the highest Q value is going to be the most likely, and ones with lower Q values are going to be less likely. But it's now some soft distribution. We're not just deterministically always choosing the same action, right? So this is a nice way of kind of representing probability distributions over a derived Q function. And we also have this beta scaling parameter, which kind of affects how deterministic this thing is. So if beta is really large, then it behaves a lot like just taking the maximum Q value. If beta is really small, then it's kind of like you're just uniformly randomly sampling actions. OK, so if we have that policy distribution, we have this likelihood function we can compute. How do we find the reward function that maximizes that probability distribution? This is basically an optimization problem. Does anyone have any thoughts? So have you guys done optimization problems yet? No optimization problems. OK. gradient ascent is one way that we're going to use in maximum likelihood inverse reinforcement learning. Have you guys heard of gradient ascent before? OK, good. Right? So if we had this reward function, and we can compute a gradient over that likelihood function given the parameters of a reward function, we can just like follow the gradient up the hill until we find some nice peak where the likelihood's very large. Right? Just classic gradient ascent. It's kind of like hill climbing, but we get to use the derivative to know which direction's up. Right? OK, but the problem with this is our probability distribution, or Boltzmann policy, depends on the non-differentiable Q function, right? Because Q values always have this max operator in there, and it's all this recursive structure, and it's just a mess. You can't compute a derivative from that. So what can we do? We can redefine the value function, right? And we can redefine it in a similar way that we'll define the policy. So this is our normal classic Bellman Q value, right? Which is basically saying the utility of some state action pair is aggregated over all the possible next states, weighted by their transition probability, and the reward you get and the value of the next state from there discounted. Right? So that's classic. We're going to keep that too. We'll keep that one the same. The normal value function definition can be defined as just the maximum Q value for the given state. And this is why we can't differentiate this, because we have this max operator and it doesn't work well. So instead, we'll define a new continuous and differentiable value function, which is basically very similar to this, except now we're doing the same kind of Boltzmann softmaxy thing, right? Where we're saying, well, the value isn't just the maximum one. It's some weighted distribution where the weight is basically some softmax probability distribution over the Q values, right? So this means we're mostly going to take the Q value of the maximum Q value, but other Q values contribute some amount to our value function as well. And so this is continuous and differentiable. So now we can compute partial derivatives from it. So that function I just expressed above, writing down the partial derivative in terms of reward function weights is kind of messy. So we're going to skip it. The Q function, though, becomes a little simpler in that the derivative of the Q values is basically the same thing, except now we have the derivative of the reward function and the derivative of the value function. And the key insight here is we have this recursive structure here, but we can use value iteration, same kind of algorithm we did for planning, to estimate these gradients as well. So we can get it all back, and now we have a gradient. We have everything computable, and now we can do gradient ascent. So let's give an example of what this looks like. So I went through that Explorer where I did things, where I moved north, south, east, west through that kind of grid world with the purple and the blue blocks and everything. Same thing of avoiding blue and getting to purple. And I saved examples. So let's run that. Right, so I have two examples here. One looked like this, right? And the other one looked like that. So basically the same things I just did. So I'm going to take these two examples, and now I'm going to throw IRL at it. So we'll see if we can read the text that comes out here. So now it's doing gradient ascent. Let me bring that back for a moment. There we go. It's doing gradient ascent over this thing, and it's pumping out reward function weights. So the reward function we gave it was a set of state features, a linear function of state features where it says I'm in a blue square, or I'm in a purple square, or like if they're all 0, then I'm not in any colored square. Right? So this is the reward function I gave it. And as it's iterating through, kind of doing this gradient ascent to the reward function space, what we're getting is different reward functions. So down here, this value here is kind of the weight associated with being in a blue square. So it's -8, which is pretty costly. The other squares have negative values, but not nearly as bad. And the last square, which is the purple, represents the purple square. You can see it gave a positive weight. So it's kind of expressing those kind of preferences where like purple's good, blue is bad, everything else is maybe not so great. And then we can kind of visualize the policy gets out of this. And we can't see where the squares are in this visualization, but you can kind of see what happens here. There was a blue square here, so it actually goes up, right? There's also a blue square here, so it goes down instead. And so if you kind of map this all out, you find it avoids the blue, and all roads lead to purple. Right? So now I get this nice generalization just from those two examples. So that's kind of the gist of inverse reinforcement learning. And there's a bunch of different algorithms we can use to kind of solve this problem, but this is one algorithm that tends to work pretty well. OK. So that's one way we can go about solving these problems, by learning from demonstration. So that's really nice if we just want a robot to kind of passively watch us, for example, figure out what we're trying to do, and then help us out. That's one good example. And it is also better than reward functions if I can just demonstrate to a robot what it is rather than having to program the reward function. But in some sense, if we're trying to teach the robot something, there's a more natural interfaces, right? Because robots are complex. So this is a PR2 robot. And if I want to control the PR2 robot to give it demonstrations, this is kind of the interface I have to work with, right? It's actually a nice interface, but not for just like your common end user. You don't want to sit here and be like, OK, well, let me grab this arm. I have to move it to this position, and then you'll roll forward this amount. It's just, it's not going to be fun to give demonstrations that way. So what would be better is kind of like a dog, right? Like I'm not going to, if I'm trying to teach my dog, I'm not going to sit there and move all of its muscles for it, right? That's just not going to happen. I guess sometimes we'll force them to sit down or something, but generally there's very little forcing control. Instead, we'll kind of reward the dog or punish the dog and get it to do the things we want. Just a more natural interface. I can just kind of sit back there in some throne, and the dog's acting, and I reward and punish it as it's doing things, right? That seems more convenient. So the question is, can we do that? Can we train our robots to understand what we want just by doing reward and function? Reward and punishment? And is that just reinforcement learning as it is now? So I'm going to try this exercise. This is shamelessly ripped from an exercise Michael Littman did. I need 2 volunteers. Philip, Lee, come on down. All right, so one of you is going to be the dog, and one of you is going to be the trainer. Who wants to be the dog? Either way. All right, you're going to be the dog. All right, Dilp, come here. I'm going to tell you the task. You have to train him using reward and punishment. Take my water bottle to the back of the room. So all you can do is, he's going to act, and you can say reward or punishment. Maybe you can say hot, cold. You can choose your words. All right? Exactly. So we can save you now if you want, or do you want to keep going?
Sure.
We'll say.
We get a long talk.
Okay. We'll save you. The task he was trying to get you to do was to take my water bottle to the back of the room.
Oh.
That seemed very hard, right? Okay. So that was hard. But what's interesting, the thing you'll notice, is he was giving you a lot of reward and punishments along the way, right? Like. If you had just waited, like in our classic MDP reward, right? If this is like Cookie Monsters, you get one feedback. You get a feedback at the end when you're done, and nothing else. Good luck, right? That just takes forever to learn anything. That's just not going to happen. So instead, humans tend to do this kind of thing, right? Where they sprinkle rewards and punishments along the way to try and guide you to doing the right thing. OK, so is that just reinforcement learning, though? Can we take our standard reinforcement learning algorithms with rewards provided by humans, so the human's the reward function, and just let them go and like have it learn? Is that going to work? What are thoughts? Yeah. Yes, you would require a very patient human. And so there's things we could do where maybe we can scale down the task. People do this with dogs all the time, called scaffolding, and make it simpler. But it's still this kind of thing where we're still giving lots of frequent rewards and punishments along the way. So even if we have a small task, like if the task was for you to simply go to the podium, you would have gotten that, right? But you still would have had reward and punishments along the way. So is that sensible? Do you think our reinforcement learning algorithms are going to work with that? So the answer is no, they don't. And the reason they don't is because you get all kinds of weird problems. So if I get a cookie, if Cookie Monster gets a cookie here, right? It's like, well, that must be a great state. And it's just like going to go back and forth between the state and there. And it's just like, well, there's reward here. And then you might say, OK, well, I'll stop giving reward there now. He did it once. He's going back. That's not good. So I'm going to stop giving reward. But the problem is now we have this kind of non-stationary reward function, which MDP algorithms don't like. They want to imagine the reward function is always the same in every state. And if you change it, the learning algorithms just like the Q values it's learning are just going to be mush. It's just not going to work well, and it's not going to get the right behavior. So this isn't really a good approach. MDPs want things like this, where like the task is fully defined by this, and that's the thing to do. So we can't use RL algorithms. So the alternative model, and this is stuff we've done here at Brown in collaboration with a bunch of other people, is we're going to use human feedback as evidence, right? It's evidence of the thing we want you to do. It's not actual reward signal itself. So we can imagine that the trainer actually has in their head some task which is well defined by a standard MDP reward function. And when you behave in the world, I'm going to reward and punish you based on whether you're consistent with the behavior you should do for that task, right? So what we can imagine is if your action that you took was consistent with the task I have in mind, then I'm going to reward you, and that means it's evidence for tasks where that behavior is consistent. If your action was inconsistent with the task, then the punishment is evidence against the task, right? So if I punish you, then clearly the task you thought you were trying to do was wrong. It's evidence against it. So it's this notion of using as Bayesian evidence. Does that kind of make sense? Let's see. So if I reward you, and that's evidence for tasks that are consistent with that behavior, and I punish you, and that's evidence against tasks that would have been consistent with that behavior, what happens if I do nothing? If I provide no feedback, right? Does that mean anything? So what about if we knew, for example, that the trainer only rewarded you? This is actually kind of common in dog training, where people don't like to punish dogs for both ethical reasons and because they think it actually is a better training mechanism to only ever use reward, right? So if we have a situation where you know the trainer's never going to punish you, and they don't reward you, does that mean anything? Yeah. Yeah, exactly. We can imagine that in some sense, maybe it's not a perfect channel, but that's maybe useful probabilistic information that you did the wrong thing because you're expecting reward. Right? So there we go. And inversely, if we know, so this is kind of like right when you turn in papers or assignments, usually it's just like marks off everywhere, right? You don't get the reward for the things you do. But so if we know a trainer only punishes you ever, they don't give you a reward, then we have this same inverse situation where a lack of punishment indicates that you did the right thing. So what we have is we have this strategy-aware Bayesian learning algorithm we created, where we're basically going to define this probabilistic model of human feedback. So we can imagine we're going to define these distributions where we want to be able to define what is the probability that I receive a reward, given that I took some state, given that I took some action, some state, and given that the actual task, was something. So like take the water bottle to the back of the room as a task, invokes certain kinds of distribution, what kind of rewards you expect for each action, right? Same for punishment. I'd have some distribution over punishment for a given state action and actual task there. And we can define this distribution by some parameters that let us kind of capture that trainer strategy where they reward you all the time or punish you all the time, right? So we have this mu plus parameter, which is basically the probability that you would receive no feedback for good behavior, right? And so that's kind of like, that's like the person, if you have a high mu plus, then the person is always a punisher but never rewards you. And we have mu minus, which is kind of like the probability that you receive no feedback for bad behavior. And then we can also have this epsilon parameter, which is like an error. Because humans aren't perfect, sometimes they make mistakes, and you don't want to just like assume that the last feedback you got was like this perfect signal. And so without getting too complex into this, that basically gives us this kind of model where we can say, well, if we have these parameters, we can define the probability of reward based on the optimal policy given the reward function. We can get the probability for that feedback, right? And then once we have this model, if we have some prior on the space of possible reward functions that the trainer could possibly, in any world, conceivably try and train you to do, then we can just use Bayes to infer what the actual task is from these reward and punishment signals that we're getting. And additionally, if we don't have these parameters, we can place a prior on those parameters and also learn those simultaneously. So let's give an example of what that means. What do I want? This is the one. OK. So this is a grid world. You can see there's actually two shades of black here. You can't tell in this rendering of it. And there's a bunch of blue boxes. And what we're going to imagine is, let's say we want to avoid any of the black boxes and go to some specific blue box. So someone pick like a blue box they want to go to. One right in the, OK. So like, maybe I should point with the cursor. It's like this guy. OK. So I'm going to reward and punish it, right? So right now, it's just kind of chilling in that blue square. So I'm going to punish it. And I'll punish it there. I'm going to give it a reward here. All right, that's bad. That's bad because we don't want it to go through black. And it doesn't want to sit there. Still going through black. Reward it. And reward it. So now he's kind of sitting there. We could terminate it. He might not have learned not to go through black yet. Let's just kind of watch what happens. Gave it some punishments for that. Yeah. It looks pretty good, actually. All right, so there it goes. So there was a huge number. There's like 192 tasks when you factor that there's two different black things it could potentially avoid and all the different goal locations it could go to. But we actually got to go that center square pretty quick with only a few rewards and punishments. So this is a very kind of nice model for getting that inference. We don't have to worry about the same situations of, I give it a reward and just trying to maximize that last reward it just saw because it's treating it as evidence for those tasks. So that's kind of the main take home here. OK, so that's training with reward and punishment. We did demonstration. It seems like, though, yeah.
Yeah, I have a question. So I don't understand what is that demo different from what you have just said. You split the reward of the way you built that.
So if we try to do, I'm just giving reward and it's doing standard reinforcement learning. Is that what you're asking?
Yeah.
Yeah. So all those rewards in between, I give it a lot of rewards and punishments. And so what that means is if you tried to solve the MDP, like using valuation given those rewards and punishments, the right thing to do would be to like go in a circle where it's all reward. Because Why go all the way to the center square when I can just go around this one local reward center that I found? And so it doesn't work out well. But because it's actually not a reward, it's evidence for the true task, which has this kind of discount reward function, like you only get +1 when you go to the goal, and you get maybe -1 when you go through the black squares. Like that's a well-defined thing where there's a clear policy that goes straight to it, and it's evidence for something like that. Or it could have been evidence for going to a different blue square. So because it's evidence, we're not trying to maximize the reward signals we saw. We're trying to infer which of those possible reward functions is the true thing. OK, so those are ways we can kind of train an agent to do what we want it to do. But it'd be really nice also if we could just talk to the agent, right? If I can just, in this example here, if I just said, take the water bottle to the back of the room, it would be clear to us, right, what the task is. We don't have to do this reward and punishment iteratively. We don't have to give you a demonstration of it. You just know. So that would be great. But then we kind of have a chicken and egg problem, which is, well, how does it know what the language means? Right? Well, we could go back to the same issue of, well, we have some programmer go in there and hard codes everything. But we're trying to avoid that, right? We want intelligent agents we can train over time. So what we'd really like to do is be able to train the agent to understand the language as we go. And then it can just follow the language after it's done some learning and understand what the words mean effectively. OK, so if I gave an example command and I want to kind of train it for these things, like what are techniques we could use? Does anyone have thought on techniques we could use to get this mapping to our commands? Yeah.
Start with very simple words and give it rewards what that corresponds with.
Interesting. Yeah, so that's like a scaffolding approach. That is a very effective approach. And you say give rewards, which is, I think, getting at the other thing. So there's two things we can kind of couple them there. One, OK, we can give a command, and we can give a demonstration of that command. And we can use IRL-like stuff to that. Or we can do reward and punishment, and we can do like the stuff we just talked about to do that mapping. So we can give this command, and we can do these things we just talked about to actually have it learn to ground what the meanings of those words are to the actual task. Because both our demonstration, our IRL demonstration, and our Sable reward and punishment let it infer the task from there. So now we can get this mapping between these two things. And so this is this is a high-level view of the model that we've built to kind of do this kind of thing. So at the top, we're going to have this kind of nice factored representation of possible tasks. And then on one side, we can have this behavioral inference and controller thing, which is basically like the inverse reinforcement learning if you have demonstrations. Or if you're training the thing with reward and punishment, you have Sable operating to handle behavior. So we can have these reward and punishment demonstrations that come out of this. On the other side, we have this natural language model that comes from these tasks as well. And you'd expect natural language commands to come out of it, like English, right? And so since we have this fully connected model, we can kind of join them together and do probabilistic reasoning that connects all the components together. That's the general strategy here. OK, so to make all this work, we want rich task representations. And by rich, I mean they're like descriptive high-level features that describe things. They're not going to be specific to every individual possible state in the world, because then we don't get generalization. I want to be able to say things like, if I say take the water bottle to the back of the room, all these words mean things. And in fact, if this world kind of changed, they'd still refer to specific objects in the world, and you can figure out what's going on. So we need some nice kind of rich representation of tasks that we're going to use. So we're going to use, let's call it object-oriented MDPs. And so this is basically just an MDP with a nice factoring of the state information. And this is actually what Burlap uses under the hood for everything. Like everything is an OOMDP. Even if it's a grid world, it's really a special case of an OOMDP. But you can do lots of kind of rich things with OOMDPs. So the way OOMDPs represent states is the state of the world is actually a collection of class-typed objects, right? So we just have some set of objects in the world. So for example, if we look at this representation of this room, one object is a robot, which belongs to the robot class. We also have room class objects. So there's 3 room class objects here. This point is green room as an example. We have door objects. So we have 2 door objects in this world. And we can have block objects. So this can be like a chair, right? Is one type of block. And each of these objects in the world are defined by their own kind of factored feature vector or state representation, right? So the robot, for example, is defined by an x and y position, which in this case has the value 2, 6 in this world. Blocks can be defined by an x and y location, a color, and a shape. So this is like in position 2, 3, and it's blue, and it's a chair. Right? So they're all just described. We have just properties describing lots of different objects, and any state can have any number of objects of any kind inside them. And the other nice thing is once you have this object-based representation, you can define nice high-level features in terms of propositional functions or predicates, right? So for example, I can define a function that's included with this OMDP that is blue and evaluates block objects. So, right? So we know is blue is true for block 1 because it has the value of blue. We can also do colors for rooms. We can also do these kind of relationship things, right? So I can evaluate whether block 1 is in room 2 by looking at the values of these two objects, right? So I can look at the location of block 1, and I can look at the spatial definition of room 2 and determine that it is in there. So I can define functions like this. So now we have a bunch of high-level functions we can also use for doing various things. So in particular, what we're going to use them for is to define our tasks, right? And this gives us a lot of generalization. So the world can look very different, but we have these nice, concise descriptions of the task despite that. So for example, we might define a task, which is by a reward function that returns 1 when block 1 or B1 is in object room 1, right, according to this function, and 0 otherwise. And similarly, we can define terminal states where the task is terminal once that block is in that room. Otherwise, it's not a terminal state. So it's a nice kind of logical representation for defining these tasks, even though the underlying representation might be continuous, it might be stochastic. It doesn't matter, we have this nice representation of our tasks we can use. OK, so given that we have this OMDP representation, let's kind of go back to our view here, which is we want nice high-level task representations to which we can connect IRL and Sable and natural language that get generated from them. So in some sense, we've already talked about this stuff, right? We have some tasks. We can do IRL. We can do Sable to do learning and inference to get back tasks from example demonstrations or reward and punishment. Let's talk about this natural language component using this kind of task structure. So to do this, we have this generative model, the probabilistic generative model, right? And you guys have done stuff with generative models already, right? All right. So on the one hand, we have our behavior, which is like IRL or Sable. Then we are going to have our language model. We'll get to that in a minute. But let's focus on the task part for now. So that's kind of these yellow. We have these 3 main yellow variables that define the task. So the first is going to be a lifted task, then a grounded task, and a set of variable binding constraints. So, and these all get generated from some initial state. So I give you the initial state of the world, and then from them we can imagine generating different lifted tasks, grounded tasks, and variable binding constraints that exist. So what do these look like? So one example of a lifted task, we kind of imagine back that room layout I had, is we might say, well, let's see, there's possible tasks that could be executed that's like taking a block to a room. But I'm going to leave which block in which room in this lifted task as a free variable. I'm not going to say which ones, because different states will have different possible block objects in them. So it could be any of them. And I don't know the names of them. I don't want to think about the names of them. So that defines some kind of class of different tasks we could have in any given state. Once you kind of selected a class of task for a given state, you can imagine looking at possible things that can satisfy it, right? So if there's a block named B1 and a room named R1 in my state in the world, then one possible grounded version of this lifted task is when we bind block B1 to the B variable and R1 to the R variable, right? And so once we have this kind of defines our reward function in terminal states concretely, and you could do IRL or Sable with that kind of thing. You can do planning with it. But we also want to get back language. And language isn't going to want to refer to things like B1 and R1, right? Those don't really have meaning. Instead, we're going to refer to properties of things to kind of refer to which objects we're talking about. So if we generate a ground, once we know what the grounded task is, we can imagine there's different ways of describing what the objects in that grounded task are. So we're calling these variable constraints. So for example, one possible variable constraint is something that's true about B1 and something that's true about R1. So we could say, well, B1 is blue, and R1 is green. So it's a green room. So this is telling us information about these things that we might use in reference. And once we have these components, like grounded task and a variable binding constraints, we can imagine constructing like a machine language from them, right? So we imagine that there's some machine language that spits out these words. It's like taking each of the names of these propositional functions, the classes they operate on, and spitting it out into the sentence. So we have like block in room, block room is blue, block is green, room. It's a machine language sentence. It's not very grammatical, but it's a sentence in machine language. And once we have this, we can imagine doing some translation from that to English, right? So we have some generative model. So we're going to be using IBM Model 2, which is a classic machine translation model. So that's like for saying, I have French and I have English. If I give you a French sentence, can you figure out what the English is? And it's a model for kind of going between those two things. And since we can generate these kind of machine language sentences from our task definitions, we can imagine this as a translation problem using IBM Model 2, where we can map words in this into words in this. And the important thing to know about this is this becomes compositional. So if I know that like is blue maps to the word blue, and maybe red maps to the word red, I don't have to see all possible permutations of together. I just have to know that that's what those things mean. And I can give a new sentence, combine them together, and I can figure out what the spit out would be. Right. OK, so given that task model, what we could do if someone says, OK, pretend I know the language, how words all map together. I know what things mean. And so someone gives an English command. And so I want to follow it. Well, since we have this generative model, all we really have to do is use Bayesian reasoning in our generative model to figure out what the task is from that command. And then once we have that task, we can choose the most probable task and just use planning to solve it, and the robot goes off and carries it out. So we can imagine if we have take the water bottle to the back of the room, you figure out what the reward function of that looks like, which is this thing being back there gives a reward of 1, and otherwise you get 0. And then there's some policy you can figure out that would, in the state, that would actually lead to that outcome. And you do it. So that's kind of trivial. And then what we want to do is we want to do learning using either inverse reinforcement learning or Sable, right? So we want to learn actually what the words mean in some sense by giving examples of commands being executed, or by training a robot with reward and punishment when we give it a command. So if I tell a dog to sit, I'm rewarding and punishing it until it actually sits, it should now, in some sense, understand what the word sit means, right? So that's what we want to do here. So if the data set we have is actually demonstration, so I have commands and I have a demonstration of that command being carried out, what we can do is, for each of our examples, each of our pairs of commands and demonstrations, we can use inverse reinforcement learning to figure out what the likely tasks are. And then we can figure out from that probability distribution of tasks what the likely machine language expressions would be. So that's just pushing it back forward through our generative model. And then that gives us this kind of pairing of a probability, machine language expression, and an English command. And then we can use what's called weakly supervised learning to take that information and just train the language model parameters. I won't get into that detail here, but then that's fairly standard. Okay. And then for learning with Sable, so now in this case, I'm going to give a command, and I'm going to reward and punish the dog until it does the right thing. It's a similar structure, except now we have this interactive situation where the robot would receive an English command. It uses Bayes to compute a probability distribution over the tasks. It uses that as the reward function prior, and then it runs Sable, right, until the task is complete. Once the task is complete, it thinks about, OK, well, I now have a good idea what the task actually was, and I can do the same weakly supervised thing of going back and using the probability of the machine language expressions with the English sentences to train our language model. All right. So let's give an example. Actually, this might be very squashed. Oh, yeah. OK, well, this was going to be hard because I can't see the text box. That's unfortunate. OK, well, I can tell you what would have happened. What would have happened is there's a text box here, and I can type in something like, go to the green room. And actually, so I can modify the state, right? So I can do things like add rooms. Here, I can change the color of them. I could type in a command like go to the green room. I hit give command, and the agent starts behaving. And then I use reward and punishment along the way. And then when it's done, it's like, OK, great, you're done. And now it uses that and updates its language model. And we do it again, and we do it again. You start to get learning that is compositional. So I can train it for things like take the blue chair to the yellow room. And I can train it for take the red bag to the green room. And then it can do things like taking the red chair to the yellow room, right? Even though it's never seen that example before because it's learned this kind of compositional structure of all the meaning of the words. And we get cool stuff from that. So that would have been the idea. You can just sit here and make these environments, move the agent around, and just interactively give commands and stuff. So just pretend that you saw the most amazing demo you've ever seen in your life. And I'm sure that's exactly what it would have been like. We're also trying to get this now running on actual robots. And that will be even more fun than watching my silly animations. OK. Doing pretty good time-wise. So the last thing I was going to talk about today then was the other side, which is this was all imagining that tasks come from humans or another robot. And so they have something in mind that they want the robot to do, and it has to be communicated in some way. The last thing we can talk about, though, is maybe something more natural, like evolution operating, right? So we have the idea that an agent that could learn the world has some distinct evolutionary advantage. But in order for it to learn, it has to have a reward function, right, that specifies what things it should be doing in the world. So evolution would have to evolve the reward function. This is very different than the classic kind of paradigm of MDP thinking, which is people tend to think of RL as there's an agent who can take actions, and then there's like the environment. And out in the environment is the reward function somehow, and the environment's sending the reward signals to the agent. But reward signals don't really exist in the world. They exist in your head, right? Your head has some preferences for things, things happen, and you're evaluating things there. And so that reward function has to come from somewhere, and it has to be evolved with us through time. So there's this interesting question we're looking at, which is, OK, so if evolution has to select reward functions, let's suppose we knew the true fitness value of different interactions in the world. Would evolution select a reward function that actually mimicked the true fitness values? And in particular, what would it do in the context of social or ethical dilemmas? So in this case, we're going to have multiple agents acting in the world. They're each doing their own learning and have their own reward function. In these kinds of scenarios, would evolution select the true objective fitness reward function, or is it going to select something else? Does anyone have thoughts about that? Anyone have predictions? No one wants to be bold and make a guess. All right. So let's ground it a little bit more. So this is a very simple problem that is extremely complex for some reason. It constantly will surprise us in weird interactions, and for various reasons I won't fully get into today. But it's at least you can think about the simple version of it fairly easily. So this is going to be this kind of ethical social dilemma, right? We're going to have player 1 and player 2. Player 1 is going to be the red guy, and player 2 is going to be the blue guy. So player 1's in the world, and it needs food, which has some fitness value or whatever. And has a decision. It can either go forage for food itself, or it can go steal player 2's food. In this case, it's a banana. Bananas are like our unit of fitness for some reason. So it can forage, and it survives, but it had to do a bunch of work to do that. It had to go around, it had to climb a tree, and that was hard. But player 2 is just sitting there. It's just right there. And it can just take its banana. And that's much easier. Of course, if it takes its banana, so it gets more reward, it gets more kind of fitness value, right, for taking the banana because it had to do less work. But player 2 is not so happy about that because player 2 loses his banana. However, if player 1 takes player 2's banana, player 2 doesn't necessarily just have to sit idly by. They can make a decision. So one thing they could do, of course, is just do nothing. They can just accept the fact that player 1 took their banana and move on in life. Or they could try and punish player 1. And they can go and they can punch him in the face. And if they punch him in the face, well, that's going to hurt player 1 a lot. It's going to kind of hurt player 2 as well. You know, it's going to maybe hurt his fist. He has to run over there. Maybe there's some chance that it's not going to go out in his favor. So it's not necessarily a great thing to do, but he could punish player 1, right? Yeah, so this is kind of our dilemma here. And we can imagine we have these kinds of, these are like the fitness values that we're going to fix. We're going to say we know these to be true. So foraging, everyone gets 0, 0. Stealing, player 1 gets +1, player 2 gets -1. If player 2 does nothing, nothing happens. If player 2 punishes, then player 1 gets -2.5 fitness, and player 2 gets -0.5 for the act of going to punch him. OK, and so this is kind of the agent model I was talking before that we now basically have. We can imagine that there's some world. The agent receives observations from the world. Those observations go through the agent's subjective reward function. So they have their own evaluation metric for how things work. And they use that subjective reward function in something like we're going to use Q-learning to learn how to behave in the world, make a decision, and their action goes back in the world, and you get this cycle going on. OK, and so if we have this evolution operating on the subjective reward function, we're going to imagine a genome that basically has 2 values. Like, one is there's a bias for theft, and one is a bias for punishment. We're going to assume for simplicity that these biases go on top of the objective reward function, because we're kind of interested in whether evolution is just going to say, yeah, use the objective reward function, or if it's going to bias things in some way. And these biases can be either positive with respect to the objective value or negative with respect to the objective value. So we can test this out. So let's see here. OK, so we can at least kind of see this interface. And let's make this 0.1. OK, so first, I'm going to let these player 1 and player 2 play this game repeatedly for a long time, for like 1,000 times, for example. Does anyone have a thought on what's going to happen? We're just going to use the objective value. So we're going to imagine both agents are using a reward function that perfectly mimics the true fitness values. Does anyone have a prediction on what the behavior is ultimately going to end up being here? Yeah. All right. Player 1 will always steal, and player 2 will always do nothing. Let's find out. And we'll scroll to the end here. And so there's a bunch of boxes here, which are, and in fact, we can't even see them all. But the summary here is exactly that. In fact, we can't see agent 1. That's unfortunate. We can't see player 2's choices. But yes, we have player 1 is going to steal all the time, and player 2 is just going to learn to do nothing. He's not going to punish. So why? Do you have a thought about why, since you predicted it?
Well, I guess like the first part kind of happens first. So player 1 is always going to pick the steal option that maximizes fitness, and then I guess it doesn't matter the order, but punishment always hurts player 2. So
Right.
like player 2, there's really like connected.
Yeah, so there's this future discounting. So player 2 can see the outcomes. And in fact, if player 2 could get player 1 to stop stealing, it would be in his benefit to punish him until he does that, to punish him every time. The fitness values are fixed in that way. But this still happens. And it is kind of this issue of, like, it's very easy to learn to steal because you get this immediate bonus, right? And that's good, so that's great. And every time player 2 doesn't punish you, it looks even better. And in learning, there's like this exploration phase where you're trying each agent's kind of trying different things. And every time player 2 tries that, he's not seeing a change really in player 1's behavior. And it's hurting him immediately in the process. So it's just a very hard thing to do to learn how to punish, even though it's like the right thing to do in some sense. So we can see here in this total performance, what happened was player 1 got lots of reward for always stealing, and player 2 just died in some sense. But we could imagine now giving different subjective values, right? So what if we gave player 2 like this big bonus for punishing? So this is like, I feel really good when I hurt you, right? Which seems strangely reflective of reality, or sadly reflective of reality. But yeah, so he gets his pleasure from hurting him whenever he's stolen from. Retribution. Okay, and now let's play the match. Things change. So again, we can't view all the boxes. But player 2, you'll notice here's minus 75 versus minus 400 something in the last game. And that's because what we now have is player 1 will eventually stop stealing. We can't, again, I can't go through the boxes because the important ones are missing. But we're finding a situation where he's just going to keep punishing, and player 1's like, this is not working out for me. He's always punishing me. I'm going to stop, and things move here. So there is this nice subjective value for that, or gain from having that subjective reward function. And so this is kind of one of the interesting things. Yeah.
How do they like sort of learn to only, like, why wouldn't agents punish all the time? Like, how do you sort of learn to punish only if it seems like you want to learn?
So in a sense, it's not learning in this case. Like when we give this subjective value of +2, it's like there's no world in which, like if player 1 keeps stealing from him, he's still going to think that punishing is great because he really enjoys it, right? So, because it's a subjective reward function, right? He doesn't care about, he doesn't know about the true fitness value. He's like, this is fantastic. I'm going to keep punching you every time. Like, bring it on. You know, it's kind of the attitude.
He also punishes you if player 1 didn't steal?
So player 1 has to steal in order for him to have a response to it. So this is a pure retributive kind of desire that we're encoding in the game. Yeah, we've looked at other models with things like that. It gets actually really hairy to analyze what's happening. This simple kind of 2-player thing we have actually gets really hairy as it is. So it's like one of the hardest 2-player games, like simple 2-player games you can imagine with like 3 states. So yeah, so it's just this, in some sense when we give this bias, he's not learning. He's just like, no, this is great, I'm always doing it. That's that. Yeah. Right, so there's this question, and so this was good for player 2 to have this kind of bias, right? To not be using the objective fitness here. And this is an interesting property, especially in multi-agent games. Because in multi-agent games, the kind of convergence guarantees you normally have in Q-learning kind of go out the window because the other player's changing their behavior. And you kind of don't want that to happen. Like, this is why game theory is hard, basically. So changing the reward function, though, is maybe a way to compensate for these hard problems that come up in these multi-agent dilemmas. So then we can ask the question, OK, so that we just did that test, and it worked out better for player 2 if that happened. So if we let this evolve, what will we see happen, right? And so we're going to use an infinite population model here. That means this is a very good way for removing noise from evolutionary models, well, a certain kind of noise, so you get the same kind of outcome of the things you know, the true optimal in some sense, it will be more biased to go to, because you don't have sampling noise and things like that. So in an infinite population, we imagine that we have all possible genomes. We're going to enumerate them. And there's an infinite population of all of them, and each genome has some ratio of that infinite population. So you can think of it as they have a probability instead of an actual frequency in the population. Then we can compute the fitness of each genome by looking at all pairwise matches between them and other genomes, and weighing that by how many of each of the agents are. So we get this total fitness by summing up all the kind of interactions they have with everyone, this infinite population. And then given that fitness, we'll probabilistically grow and shrink their ratio in the world based on how well they did. So people who had much larger fitness than everyone else is going to reproduce a lot more, and their ratio in the infinite population will grow. Right? So what are people's predictions about what will happen here? We run this model. All right. Uncertainty is probably a good thing. So we kind of see what we saw with that bias initially. So what happens is, because learning to steal is fairly easy, I should explain this diagram. This is like a heat map where along the x-axis is each generation of the evolution. And then each of these guys represents our genome. So this is the bias on punishment, and this is the bias on theft. And then very blue, whitish blue means a high population in that time step. And so what we see here is these genomes here basically represent an agent that's very flexible for theft. So they can learn to steal, they can learn not to steal. but they have a high subjective bias to always punish. Right? And initially, they surge in the population when things start. And they surge because stealing is pretty easy to learn to do, so we can be flexible there and adaptive. But punishing is hard, so we're going to have a high punishment bias. And so that grows very quickly. However, there's this interesting switch, which is once the population kind of homogenizes and you have everyone is basically a punisher and a flexible stealer, there's no more reason to learn to steal anymore. And there's no more reason because there's some small cost associated with learning to steal. And since everyone's a punisher, you're going to ultimately not steal anyway. So now we switch to this population of people not stealing and always punishing. And things actually can drift further from there because of all these homogenization issues. So we kind of asked the question, though, well, in reality at least, lots of people still steal. We didn't have this switch to no one ever steals. And so we thought about, well, are there certain reasons that might be true? Like why that might stick around in the population. And I'm kind of low on time, so I'm just going to go through these. We kind of came up with two possibilities. One is evolution in the real world is always kind of throwing in this pool of suckers. Right? So if there's always suckers in the world, learning to steal is good because you can exploit them and stop the others. And also, there's situations in the world where you might be able to get away with stealing. Like you know the person just has no chance of knowing who you are, and so it's like safe to steal. And so in that situation, you might have this kind of learned preference for stealing or not stealing that still exists. And so what we did is we reran our model with those kinds of assumptions. So we can imagine there's special states in the world the agent can reason over where it can figure out that it's actually safe to steal because the other guy can't punish. And we did the same thing where we said, or we'll let some population, some mutations sign up. There's always some population of suckers in the world. And now you get this very stable switch to having this flexible theft and this resolute punishment kind of bias for retribution. So we see that kind of come out. All right. So since we're just about out of time, our overall conclusions of this talk, the main point you should get is people who do MDP research usually are just focused on getting out of policy. But there's a whole lot of other important questions about where the reward function that those things just take as input come from. Right? So there's learning from humans. Right? So a human wants a robot to do something. It has to communicate it either by demonstrating what it is they want to do, by rewarding and punishing themselves, which is different than reinforcement learning. Or they have to learn you have to train the agent to ground commands so you can just speak to it in the future. And also we talked about how evolution may play an important role, especially in these multi-agent situations, about pulling out these reward functions that kind of bias the right kind of behavior and learning. We also used burlap in a lot of these demonstrations. So if you want to do a lot of the things we did, you can check out burlap and do this stuff yourself. So